title of our notes today are the mole and its mass. So the first question I have to pose for you is, how many pieces are in a dozen? 12 pieces in a dozen. How do you know that there are 12 pieces in a dozen? Well, it's just something you know, right? A dozen is a quantity, and that means 12. Okay, what about a pair? How many is in a pair? 2. Okay, how do we know? Well, it's just something we learned, that a pair means 2. So today I'm going to introduce you to a quantity that is a human-made construct. Like, a dozen isn't something that, oh, that's just something we find in nature, a dozen. It's a convenience measure. Oh, I want a dozen of this, a dozen of that. It's for convenience, and humans made it up. Okay, it's the same with the quantity that I'm going to share with you today. So that quantity is the mole. So a mole, hi Miss Moss, no, it's okay.
Are you busy?
Yes, I am.
Hello!
Yeah, right.
A mole is in the ground and digs for, oh no, not back to the mole. They'll have to revisit this in AP Bio too.
Okay, so there's nothing that was pressing right now that you needed to
Not
know?
whatsoever.
Oh, okay.
What's Avogadro's number again? Oh yes.
Okay. All right. Wow, did I leave that off? Oh, I did. I'm going to have to write it down. Boy, I'm glad she said that. Okay, a mole, how about that abbreviation, mole? A mole represents 6.02 times 10 to the 23rd pieces of something. Okay, that's a lot. That's a lot. All right, so let me write this down, this next bit. Cricket, these aren't in your notes. You're going to need to write this down. This number, is also known as Avogadro's number. Named after an important Italian physicist who is commemorated with this quantity, who did work that led to kind of this thinking, but that's off the topic. Okay, so a mole, 6.02 times 10 to the 23rd, is also known as Avogadro's number. All right, that's a lot of pieces. Okay, so, like a dozen is always 12, a mole is always 6.02 times 10 to the 23rd. Okay, and that could be 6.02 times 10 to the 23rd pieces of anything, just like you could have a dozen eggs or a dozen bagels. You could have a mole of anything. It's just that's how many pieces are in a mole. All right, now this, in this jar right here, this is a mole of carbon. This is a mole of carbon. There are 6.02 times 10 to the 23rd pieces in this of carbon. How do I know that? Did I count it? Did I count that many pieces? No, I did not. So in chemistry, we actually count by weighing. Now, why would chemists come up with this monstrosity of a number for a quantity. Why? Why, compared to a dozen? That's a lot. And that's because, of course, atoms and molecules are so tiny. They're so tiny that we need lots and lots of pieces of them in order to actually see them and manipulate them. Okay, so again, I know that this is 6.02 times 10 to the 23rd pieces, and actually I can say it now, atoms of carbon, not because I counted them, but because I weighed them. Okay, now, does that make any sense at all? Probably not. The periodic table lists the mass of 1 mole of atoms of an element. Atomic mass represents the molar mass of the element. Okay, so this part can be extremely confusing. Because the mole is a human-made construct. Chemists made this extremely convenient. So when they came up with the idea of a mole as a quantity that we can use in chemistry, this is how they decided. They took exactly 12 grams, okay, so not the average, they took exactly 12 grams of the isotope carbon-12, and then from that 12 grams of carbon-12, they were able to count the number of carbon atoms that were in that sample of carbon-12, and they came up with this number of 6.02 times 10 to the 23rd. And so we say that we are on a carbon standard, okay, because that's where the number, Avogadro's number, the mole, came from, is from taking 12 grams of carbon-12 and counting the number of atoms that are in 12 grams of carbon-12. And so this ingenious idea now because all of these atomic masses are relative to one another, we can now extrapolate that to being moles. Okay, so for instance, if I want to know how much a mole of just typical carbon, taking into account all of the isotopes of carbon that we find on this planet, how much does a mole of carbon weigh? What is the mass of 1 mole of carbon? 12.01. Okay, because remember, in this instance, you guys were taking into account all the isotopes of carbon. How much does 1 mole, what is the mass of 1 mole of nitrogen atoms? 14.01 grams. What is the mass of 1 mole of oxygen atoms? 16 grams. So this number on the periodic table, atomic mass, can represent 2 different things depending on what our units are. It can represent atomic mass units being the typical number of the mass of, or the number of protons plus neutrons in the atom. But because of their ingenious way of coming up with what is a mole, it also can tell us how much 1 mole of this particular element weighs. Okay. The periodic table lists the mass of 1 mole of atoms of an element. Atomic mass represents molar mass of the element if we are using the unit as being grams. Okay, so for instance, the molar mass of carbon. Carbon is 12.01 grams per mole. This is what the unit looks like of molar mass. Grams per mole. Oxygen is 16.00 grams per mole. So, how do I know that this is 6.02 times 10 to the 23rd atoms of carbon? I just weigh out 12.01 grams, and I know that that's how many pieces there are. So using this, we can do all kinds of problems. So let's do some. So our first one is calculate the number of molecules in 0.350 moles of glucose, C6H12O6. Okay. So, to do this, we are going to begin with what is given, and that is 0.350 moles of C6H12O6. And we're going to put it over 1. And now what we need to think of is we are looking for the number of molecules. What is a new conversion factor that we have learned today that can take us from moles of something to the number of pieces of something? Either the number of molecules or the number of atoms. Okay, that's Avogadro's number, which is, okay, so I'm going to use some dimensional analysis here, 6.02 times 10 to the 23rd molecules of C6H12O6 per mole. And we can put per 1 mole. Okay, so again, it's like a dozen. It doesn't matter. You can have a dozen eggs. There's 12 eggs per dozen, 12 bagels per dozen, 12 donuts per dozen. 6.02 times 10 to the 23rd molecules in every mole. So then we're going to cancel our moles, and that is going to leave us with the number of molecules of glucose. I want you to do this on your calculator. I want you to calculate it, and when we get to class tomorrow, we're going to check to make sure that the answers are right. To make sure that you know how to actually put scientific notation into your calculator. Okay, this is one kind of problem we can see with our new conversion factor. What if we don't want to know how many molecules 0.350 moles represents? What if we want to know how many hydrogen atoms are in 0.350 moles of glucose? So now I'm just going to go one step further in my dimensional analysis. I'm going to begin with what I'm given. 0.350 moles C6H12O6, and I'm going to put it over 1. And then I'm going to go to molecules. 6.02 times 10 to the 23rd molecules of C6H12O6 for for every 1 mole of C6H12O6. And then I'm not looking for molecules. I'm looking for hydrogen atoms. That's what needs to be in my numerator at the end. So these moles are going to cancel. So how am I going to go? So I've got to cancel out this molecule. So I'm just going to put it in my denominator. Molecules of C6H12. Would have been better if I used a smaller molecule. O6. Okay, for every 1 molecule of glucose, how many atoms of hydrogen are there? Because that's what we're looking for. Atoms of hydrogen. Okay, in this molecule of glucose, for every 1 molecule, how many hydrogen atoms are there? 12. So there are 12 atoms of hydrogen for every 1 molecule. Okay, and so then I can cancel my molecules, and you're going to calculate it. All right, let's do some more. How many sulfur atoms are in 16.3 grams of sulfur? Okay, so we're going to use a couple of conversion factors now in this one. We're going to begin with what we're given, 16.3 grams of sulfur, and we're going to put that over 1. Now, we cannot go from grams to atoms. We can go from grams to moles, and then moles to atoms. So, if we've got this many grams of sulfur, what conversion factor are we going to use to go from grams of sulfur to moles of sulfur? We're going to use the molar mass of sulfur. Where are we going to find the molar mass of sulfur? We are going to find it on the periodic table. So we're going to go to our periodic table. We're going to find sulfur, which is here. And the molar mass of sulfur is 32.07 grams per mole. .07 grams of sulfur for every mole of sulfur. Okay, the number always goes with the grams. It's like the number per dozen. There's not 1 egg in 12 dozen. There's 12 eggs in 1 dozen. Okay, it's the same with this. The numeral always goes with the grams. 32.07 grams per mole, for 1 mole. All right, so now our grams can cancel. But we don't want moles of sulfur, we want atoms of sulfur. So, do we have a conversion? Yes, we do. There are 6.02 times 10 to the 23rd atoms of sulfur for every mole of sulfur. So our moles will cancel, and then you need to calculate the answer. 16.3 divided by 32.07 times 6.02 times 10 to the 23rd. All right, we have one more thing that we need to cover. And that is, what if it's it's not an element? What if it is instead a compound? How do we find the molar mass of a compound? So the molar mass of a compound is the mass in grams of 1 mole of that compound. And so for something like water, how would we find the molar mass? Or, in other words, how much does 1 mole of water weigh? Or what is the mass? What is the mass of 1 mole of water? It's molar mass. Okay, and so what we do basically is we take the molar mass of all the individual constituents and then we add them together. So in this case, we've got 2 hydrogens and an oxygen. So we're going to say, okay, if we've got 2, we have 2, and the molar mass of hydrogen, if I go to my periodic table, is 1.01 grams per mole. So there is the contribution from the hydrogen. I have 2, and that's the molar mass of them, plus the contribution from the oxygen. How many oxygens do I have here? 1. And the molar mass of oxygen is 16.00. So if we add this up, the sum is 18.02 grams per mole. And that is the molar mass.